Good. So today we're going to talk about Delft3D Flexible Mesh, which is basically the next generation Delft3D. So what you have been working with till now is Delft3D 4, which is a structured version, which was developed in the early 90s. And starting around 2010, the new version of this, so Flexible Mesh, was developed by Herman Kernkamp at Delft3D, who's a colleague of mine now, because, well, people who don't know me, so the most people do know me, but other ones don't. My name is Jan Rijns. I work as a lecturer at the Coastal Engineering group. I work 3 days a week at IG as a lecturer, and 2 days a week I work at the Applied Morphodynamics department at Delft3D, where I mainly work on developing this model. I write the code for 2D, 3D width and morphology. So that's a large part of my job. So hence I was volunteered to give a presentation on this. So where are we in the grand scheme of things? So this is a schedule for this week, and we are Thursday morning. So we're looking at Delft3D FM. I will stick to hydrodynamics. I know it's a morphodynamics course, but to keep things simple and because the learning curve is rather steep, we start at the beginning. So we're going to do simulations of simple hydrodynamic flows. Exercise 5, though, in the second period, is a exercise that's a little more complicated, and that also involves morphology. And it's largely the same as, I think, the breakwater case you did yesterday when you did Delft3D 4 modeling of waves and a flow model. Did you couple that? Yeah. Well, that's the flexible mesh equivalent with a little morphological change. So that's nice. Okay. So to fire off this lecture, I have a nice screenshot of an interface that's very familiar by now, I think, if you just spent 10 minutes clicking on the Flexible Mesh suite shortcuts. And my question to you is, if you compare this to everything you have seen from Monday to Wednesday, what is different?
The grid.
That's what is different about the grid?
It's not rectangular or not. It has different shape, not like the one we work during the week.
It's not one mesh, it's one grid. It's
a combination.
It is one grid. But indeed it's true, so the shape of the grid is different, and you have different elements. What else do you see?
The map.
The map, yeah. We have fancy GIS tools in the new user interface. That's also a huge difference.
I think the area of interest has a smaller grid size than the out
yes,
of the board.
So, and do you see what? So, if you relate what you have seen previously to that observation, what do you see in terms of improvement?
Layers.
What do you mean by layers?
Like in the window on the left side.
Oh,
yeah, we can put many layers.
Well, those are actually, these ones are actually so this is just your normal set. But normally on this side you see chart and map, and here you can indeed click on and click off layers, so you can visualize your model very nicely. That's true. What else do you see?
The grid can go with the curve and this structure.
Yeah, it's really nicely boundary fitted. That's indeed also a difference with Delft3D, where you have here you see it very clearly. So you have small triangles that are sort of cut off and nicely follow indeed this breakwater that is lying there. So that's indeed another one. So you don't really have the staircase phenomenon here, like you would see in a structured grid.
And the map itself.
And the map is really nice. OpenStreetMap supportable. Okay, so I think that we indeed have touched upon some important aspects of what we're going to talk about this morning. So indeed you have different elements. So you have rectangles and triangles, and you have refinements in different areas of the grid. And what's important is that those refinements don't affect the rest of the grid. A really big, important difference. Indeed, it's nicely boundary fitted, so that's also an advantage. And you see that you have nice resolution transitions, so that do not spread out in the rest of your grid. And indeed, the interface is better, so you can actually visualize your study area and make your grid a little nicer compared to just using non-boundary files in RGF grid. Okay? Any questions here or things that are not clear? No? Cool. So that brings us to the objectives of this morning. So what I want you to retain after this lecture is first to get some grip on what the modeling philosophy is when you use Delft3D flexible mesh compared to Delft3D 4. Secondly, I want you to be able to assess when you would use Delft3D flexible mesh compared to Delft3D 4, because the fact that flexible mesh is available does not mean that it's actually always the better option. So if you have both available, there are situations where you're better off using Delft3D 4 than using Delft3D flexible mesh. That usually comes as a big surprise to a lot of people, but it's true. And thirdly, I want you to be able to set up your own basic little hydrodynamic flexible mesh model by the end of this lecture. Yeah, so that's our goals for today. So how are we going to do that? First, I'll tell you a little bit about the background principles of Delft3D, and then the second period. Oh, sorry, that didn't go well. In the second period, so first we're going to make our own unstructured grids. Then we're going to do an exercise where we actually impose boundary conditions. So we're going to impose water levels and discharges on an estuary model. Then we're going to run it and visualize a little bit the results in Delta Shell and also in QuickMod. I hope you still have Delft3D 4 on your laptops with QuickMod working. Good. All right. So, what is Delft3D 4? I don't have to repeat that. So that's a structured hydrodynamic and morphodynamic modeling suite. You have spent 3 days now working with it, so I think you have a fairly good grip on what it can do and what it cannot do. We had extensive lectures on that. So next to that you have Delft3D flexible mesh. So first of all, the big difference is that this is a structured grid modeling. Flexible mesh uses unstructured modeling. And I use these terms a lot, and I realized that I didn't really explain it in my lecture what the difference is. So if you have an unstructured grid, so let's start with the structured grid. So this is what you have seen. So if you have a structured grid, you have a grid. So, and every grid cell has a row number and a column number. Yeah? So every single has an end coordinate. You also saw that when you did a refinement in RGF grid, you could say an refinement factor and refinement factor. Well, that relates to this thing. And if you're in a structured grid, then every cell, because of it has these n and n coordinates, knows exactly where it is in the matrix. So you ask it, what is your 10th neighbor to the left? Then you know, well, that's n plus 10. Right? So, and your whole matrix is built up like that. So every cell knows exactly where it is in the matrix, and you can query like everything. The downside of that is that you cannot just split this into, because then your whole numbering would go haywire. And you can also not just take away one column, because then of the same reason, right? So that's why if you refine a structured grid, so if you have this and you refine it like here, then you have to refine it over all the columns. And if you want to refine a column, then you have to refine it over all the rows. Right? You saw that when you made that wave model. You know, you had a little zone of interest where you needed more resolution. But as soon as you refined that, you saw that that spread out over the entire domain. Yeah? So that has to do with this matrix structure. If you're modeling unstructured, then you have for example, a triangular grid, or a combination of triangles with rectangles, like so. So here again you have cell centers, like so. Let's complete this to rectangles, like so. So this cell here is triangle. This one only has knowledge about its neighbors. So this cell here, the only thing it knows is that this is a neighbor, this is a neighbor, and this is a neighbor. It doesn't even know that this is a neighbor, or that this is a neighbor, or that this is a neighbor. And this is really good because that means that you could, for example, split this, and this would be a new neighbor, and we have two new cells. And computationally, that doesn't change a thing. It's only a lot more difficult to code it. But for the user, it's super easy because you just make a grid, you draw a polygon, you say refine, and you can all of a sudden double the number of cells or half the resolution. You create automatically your connection triangles, and you basically have a new grid. And every cell is still happy because it just has to know its neighbors to be able to do the computational activities or computations. Okay? And then this is then not only in terms of geometry, but you could also combine 1D, 2D, and 3D approaches with using this.
In the structures grid,
Yeah.
we asked a question about the instability of the model, and that may one cell only give, for example, depths for 10 meters, or which is not making sense. If it happens here, that means that it will affect the neighbors. Like here, the error can be one cell. Model stability for one cell here, but here it will affect the others.
Well, I don't see why one instability here will not affect your neighbors. Any instability will soon spread out, no matter what you. I did not understand the question.
No, the question is like I asked about like what is the like how to know that the model is stable or not, and one of the cells may come with like for example huge depths compared to the other, so this cell alone is unstable. Or I'm misunderstanding, I don't know.
Well, that doesn't happen a lot because on Monday you had your lecture on sediment transport equation and the bottom update. And there you saw that actually the change in the bottom, so your delta z is a function, so in a cell, is a function of the, how do you say that, the gradients in the transports. So what that means in terms of this is that if you have a bottom change here, then that is related to all the sediment fluxes coming over the sides of the cell. Right? So if you have an instability here, that is then related to one of these transports being crazy. And that automatically almost means that also these cells will be unstable, and that will spread out very fast. So usually these instabilities will not be very local. In flexible mesh, we have seen that it is that is the case, that it is very local, but that was usually because of underflows, because we divided by a cell volume that was too small or something. So then you could have that. But the Delft3D is very stable in that regard, so I don't expect that to happen.
Okay.
Yeah. unstructured, we're working with 1D, 2D, and 3D in one grid. So that means that you could have a 1D branch like so, that is attached to a 2D grid, that is attached to a 3D grid with 10 layers, for example. So you can have that in one model grid. Yeah. So you don't have to make separate grids, models, you don't have to do domain decomposition, none of that sort of things. Okay, so the big advantage of that is you make your model once and then you can easily adapt it. So you don't have to redo the entire model because everything is basically in geographical coordinates. So you could just delete the entire grid, remake a new grid, and for example, all your boundary conditions would still be valid. Yeah. So that is very cheap. And just as Delft3D 4, that's not really a difference, but you can couple with other models. So stuff like water quality, waves, real-time control that control the movement of structures, sluices, gates, and so on, based on certain signals. So you can do that also with flexible mesh. Okay, and then one thing that flexible mesh has compared to Delft3D 4, which is really nice, is that it is BMI compatible. And BMI stands for Basic Modeling Interface. And what that means is that you can implement, I think, 40 functions or so, and then make your model BMI compatible, they call it. So that you have that for different programming languages. And then two models that are actually so-called BMI compatible can talk to each other. So you can run one, that gives data through memory to the other one can do something with it, give its own data back to the other model, so they can actually talk to each other in memory, which is very efficient and very cheap compared to writing files and then reading files, and give files back, reading files, like we do in Wave, for example. Yeah? So one example of that is this is the MSc work of Oding at the University of Twente. This is based on a BMI Python model that was developed at Delft3D, that also is being used here by Mick and his PhD students, among others. That couples actually a vegetation growth model, so this is the upper row here. So this gives the evolution of vegetation through time, and it couples it to a morphological Delft3D FM model, which you see down here. So you see actually that vegetation determines the position of the channels, and then the position of the channels determines further evolution of the vegetation pattern. So you have this feedback mechanism that's going on. And you can do that because you have a tight online coupling between the Python vegetation growth model and then
So
yeah.
this is modeling or simulation by Python and Delft3D FM?
Sorry?
Like this is two models like...
Yeah, so this is a Delft3D FM model, and this is basically a Python script. And through the basic modeling interface, this Python script can ask for arrays from FM while FM is running. It can take those values, do its own calculation for the vegetation growth, and then it writes resistance files or resistance information for the flow model and sends it back to FM. And then FM can do its own hydrodynamic calculations and morphodynamics based on those roughness values, give updated flow fields back to the vegetation growth model, which can then calculate a new growth step, and then give back the roughness and so on. So you have a back and forth communication, really tight, nice coupling, with nice results. So this is a big advantage of Delft3D Flexible Mesh compared to Delft3D 4. As I said before, the biggest advantage is that all the model input is in geographical coordinates. So you don't have to fiddle around with M and N coordinates anymore, and whenever you decide to add two grid rows, that you have to redo the whole model setup as before. So here you just draw a polygon, and if you change or refine a grid, then this polygon is still valid for that same grid. Yeah? So like I said, that makes the usage a lot easier, but for us poor coders, think about the coders. Okay, so what sort of networks are we looking at? So like I said before, you can combine a 1D network, so this is what you see here. So you see a 1D network and also here, but there's several branches. These coupled to a 2D network here, so you see these little connection links. So these attach to cell centers of 2D cells, and then you have a curvilinear part here. So you have a curvilinear part here, which is nice because it's fairly accurate and it's also fast and better than triangles actually. And then all the floodplains, well, you can fill those up with other geometric elements. So you can use triangles to do connections, and then you can use hexagons here because that is a geometric element that covers the most, or you need the least amount of geometrical elements to cover an area. That's a mathematical law, I think. And also here you can use rectangles. So you can have all these different geometries in one grid, and you can actually use the most suitable geometry for the how do you say it? You can always choose the most suitable geometry for the given problem within your model. So here it might be conveyance of your river, and then here it might be floodplain inundation during a high flood peak. Yeah? And then one very, very, very important remark. Flexible mesh is an explicit model. So, unlike Delft3D which is semi-implicit, so I don't know whether Dado told you how that works? No? Okay, so Nick told you Tuesday that this maximum CFL condition in Delft3D is 10. And that is because Delft3D solves its system in 2 half time steps. So you have 2 directions. You have this n direction and this n direction. So what it does is in the first half time step, it solves the one direction implicitly and the other direction explicitly. And then in the second half time step, it solves the other direction implicitly and the first direction explicitly. And if you do that, then you can work with higher or bigger time steps because it's a semi-implicit way of solving it. It's called the ADI scheme. Flexible mesh, however, is fully explicit, so it has a strict CFL smaller than 1 condition. So time steps in flexible mesh will, in general, be smaller than in Delft3D. That's what you have to remember about it. Yeah? That also means that there are always cells that are limiting your time step. And often, with some careful judgment, you can make your model faster by removing these cells or making them, position them better, or changing the bathymetry slightly. But usually it's one little cell that actually makes your time step very small. So whenever you set up an FM model, make sure that you find that cell and see whether you cannot do something about it, that your time step actually can be bigger. Okay, so that is the first big difference or advantage of Delft3D FM. The second one is something I also already talked about. So this is a structured grid. So these are actually 3 wave grids that I took from a project at Altaris. And we progressively refined those. And the only way to get the resolution, so here actually is our zone of interest. And we need enough resolution here to actually solve our flow there. And the only way to get that resolution here is by refining, and you see that these refinements spread out in the rest of the grid. Yeah? So it's already bad here, but here it's even worse. So now I'm modeling here at a 5 meter crossover resolution where I don't need it. Okay, so this is actually a waste of memory, computational space, and time. Okay, so So in flexible mesh, you have more options to not have that issue. So this is the same original grid as the first blue one. So you can refine in a number of steps. So you can do a local refinement here, you can do that twice here, and you see that you have nice connection triangles, so your refinement doesn't spread out in the rest of your grid, and you can happily only model at fine resolution where you want to do that. You can also choose to do that with triangles that vary in size over the domain. So triangles are smaller here than they are here on the boundaries. Or you can choose to do, well, these are two academic cases, so a very fine uniform grid and a very fine uniform triangular grid. But usually when you refine, it will do something like this. Yeah? With the advantage that you don't have this spreading out of superfluous fine resolution in the rest of your grid. So that's the second big advantage. So, of course, people have tried that. And I heard there's a lot of river people, so these will be very happy to see this. This is a very famous river bifurcation in the Netherlands. This is the Pannerdense Kop, which is south of Arnhem. So here is the Rhine River, and this is the Waal River. This is the Rhine, so this is the Nederrijn, Pannerdense Canal, I think it's called. So here you see that on the Rhine itself you have a fairly coarse resolution, and then you want to keep the same number of cells that you have here in your conveyance area, here for the Waal and also for the Nederrijn. And then all the rest are floodplains, so these are modeled at either the same resolution or somewhat coarser, because you don't always need high resolution there if it cannot flood, for example. Yeah? So this is one example of a Rijkswaterstaat project model. From the same project, we also have this. This is one of the most beautiful grids that I've seen in my life. I mean, this is art. I've honestly have pondered about printing this and hanging it in my living room. Because if you come from a structured grid background, this is impossible to make using structured grid. So this is art. This is a part of the Waal, I think. So you see that the actual river is done nicely with a curvilinear grid as before. And then to model well, you also see that the grid lines are nicely aligned with all these little groins. And then to model the floodplain, actually, you have a coarser grid. And these are also nicely aligned with triangles. But the nice part is that this is actually nicely continuing, and also the grid actually changes direction within this little area here. So you actually, yeah, it makes like a 90-degree turn. It's so ingenious. This is you can keep looking at it. It's brilliant. I really advise you to have a look at this slide for 5 minutes or so. It will be odd. Okay. Another example is one of the earliest FM models was one of the larger North Sea. And this is a typical example of a Courant grid, because this model was made to simulate tides, and tides have a wavelength of, well, typical M2 tide is about, Ali, how long is an M2 tide? Is there a language?
Around 600 kilometers.
No, it's long, it's about 1,000 kilometers, 900 kilometers. So what that means is if you have to resolve a wave, so if you have to resolve a wave shape, so from here to here, you basically only need like 15 points or so. So if this is 1,000 kilometers, well, your grid resolution can be extremely large, basically. So that means that the size of your grid cells, in this case, is determined by your current number, right? Because you can model the tides pretty well with an extremely coarse resolution. But if you have large cells, then you can, based on the Courant criterion, you can always impose the largest cell given your Courant number. Do you understand what I'm trying to say? So if the physical process that you want to model doesn't dictate your resolution, you can have the Courant number dictate your resolution, and you can always work with the largest grid cell possible, given a certain depth. Yeah? And that's what's demonstrated here. So, so in very deep water, you can work with gigantic resolutions, and if you go finer, then you can still work with fairly coarse resolutions. Yeah. But it's all dictated by your Courant. Yeah. So it's not a Courant grid is a grid where the physical process doesn't dictate the grid cell size, but it's actually the maximum grid cell size that you can use there based on the Courant criteria. All right. Then I have a last example that Mick talked about on Tuesday, but using Delft3D. Mick, if you would do this whole exercise again, what would you use? Delft3D or Delft3D? An honest answer, please.
Oh no, obviously flexible mesh, sure. I mean, otherwise it would not be possible, actually.
No, I mean, if you would do your San Pablo exercise again.
That's a smaller grid.
Yeah, but you still have to make the entire model to derive the boundary condition.
Well, at this moment I would use flexible mesh, but 10 years ago it would be Delft3D.
10 years ago we didn't have morphology of flexible mesh.
No, but for the boundary conditions,
yes,
and the tidal propagation. Well, the problem here is of course the delta area,
yeah,
where you have all these networks connecting to each other, and if you want to make a Delft3D grid on that is basically impossible.
Oh, we did it once for the Bangladesh, the Magna. That was a lot of counting. Anyhow, so this is a brilliant example made by Mick and Ali of indeed San Francisco Bay. So here you can see indeed the delta with all the channels, and now all these floodplains are also filled up in the grid, I think by now, to allow for flooding of these. But yeah, so as you can see here, this would be hell to do this with a structured grid. You would need domain decomposition, and you would have to count rows to make the correct attachments, and don't get me started. I've done, like I said, I've done it for Bangladesh, for the Magna Delta there, and it took me months of time, and it's really like I'm now in the 145th row, and it should attach to the 154th cell over there, so I can use 3 cells wide to actually make that connection. So this is brilliant. Okay. So before I start on the conceptual framework of what is behind the scenes, are there any questions about what I've been telling you? Things that are unclear, that I have to re-explain again?
You said we will have an idea about how to choose between if I'm going to use Delft3D 4 or flexible mesh. So except for the condition of less than 1.
Yeah, the CFL condition. Yeah.
What is else can be judgmental in this area?
Well, for one, the grid creation. Let's say that you're an engineer modeling, and you get an assignment from a client, and they ask you to evaluate the morphological effect of outlet of a electricity power plant. Say, and so you have an outlet, and that's protected by little groins against scour and so on. But they're not really sure yet how they're gonna design it. So whether it be long, short, where they're exactly gonna put it. So if you would be using Delft3D and you make a model of that, and you run it, and you say, well, that's not optimal, blah, 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 that doesn't meet the criteria that you proposed. They have to go back to the design table. They have to make a new design. They may be relocated. So you have to make your refinements and your grid somewhere else. That means that you have to redo your boundary conditions unless you take the exact same number of rows and columns. So if you do a refinement somewhere else, or you do more refinements, it means different boundary conditions. That means a new bathymetry. That means, so you have to redo everything. Well, if you use flexible mesh, for example, then you can keep your boundary locations at the same position. And you can change your grid locally. That doesn't matter. And you can still use the same boundary. So you can shift your grid, refine it, you can cut out pieces, you can do whatever you want. But you don't have to remake your bathymetry, your boundary conditions, your battery files, your grid. You don't have to count, you don't have to. So it's not really to do a lot of modifications or make a lot of variants of the same problem.
So basically, if you don't know what's waiting for you during the project, you choose the
You choose what costs you the less money. And in this case, if you know that the functionality is really good and it gives you reliable answers, then I would take flexible mesh. But then again, also time steps, or so if you have for example, a problem where the geometry is more or less fixed, so the chances that you will have to adapt the grid are fairly small. So the grid, building the grid is a one-time operation, and you only have to vary the boundary conditions or these different scenarios. Then you could choose Delft3D because if you design your model a little optimally, then you could use probably bigger time steps than flexible mesh. So you can run faster for the same problem. So it all depends. Yeah. And then if you are looking at a problem that combines different physical processes that have different spatial scales, not only horizontally but also vertically, yeah, then it's cheapest to use it. Because then you can combine a catchment with a delta area in a 3D estuarine environment, where you have salt intrusion, and then the delta you might have just a freshwater river flow, and then upstream you might have catchment dynamics that can perfectly be captured in a 1D model.
Can we shift, if we started with one of them, like let's say with the FM, and we figured that it's not good enough or something, can we just convert it or send it to 3D?
As long as parts of your grid are curvilinear,
yeah,
you can always change the grid. But you will have to then use domain decomposition or so to actually merge the domains together into one model.
okay, and if the grid is not curvilinear,
No, then you can.
but we cannot send everything and just
No,
like
because
create the grid
you
all
need
over
this-
again?
You need this sort of administration.
So we need to start from scratch.
Not always. So if parts of your grid are curvilinear, then you can convert them from an unstructured grid to a structured grid. So you can reuse those. But you would have to make, you have to adapt your grid so that it nicely attaches. And you adhere to this concept. Yeah.
I just want to ask that this flexible mesh is a totally independent software from the Delft3D.
Or
For yeah.
No.
Just used to
Well,
make the
well, largely in terms of hydrodynamic kernel, yes. But there are modules that we share, actually. Like the morphology module to calculate sediment transport. That is shared between Delft3D 4 and Computational. But then how the bottom update happens, that is specific for every model, because that has to do with the geometry of the grid. So there are things that are shared. For example, the wave model, D waves. That's
so
also
only
shared.
hydrodynamic model they don't share.
No. So the hydrodynamic kernels, they are separate.
Oh.
They don't share code.
So other thing for
But
morphology,
well, waves is structured and communicates with files to flexible mesh, as it does with Delft3D 4. So it uses a different interpolator, but the concept is the same. Water quality can only work offline with Delft3D 4, but there is now an online version of flexible mesh. So you can do for water quality simulations, you can do them inside flexible mesh. It's just a flag that you can switch on. So you don't have to do first a hydrodynamic run and then do a water quality run, but you can do it in one run. Yeah. So some things are shared because we estimated that it's just as well working with flexible meshes as with Delft3D 4. But others are conceptually not you cannot reconcile them. So you have to write something separate. Yeah? Any more questions? You? Entitled to a break, I think. So shall we